Hello everybody and welcome to another online seminar presented by Acoustics. My name is Jacob Sondergaard and I will be your host today. So today's topic is going to be about acoustic end-to-end measurement. And if you're watching this, then of course I would also advise you to check out our YouTube channel because we have many more online seminars available for you to review. Regarding telecommunications testing in general, certainly a lot of them are focused on audio conferencing capabilities. This one is going to be related to that, but there's going to be some new stuff here. The agenda that we're going to cover today, we will of course talk about the traditional measurement setup, the one that we're familiar with, mostly familiar with, that is the electric to acoustic scenario. And then we'll dive into the acoustic end-to-end setup because we'll talk about where we use and where acoustic end-to-end setups are applicable. And then we'll talk about some of the challenges and benefits of doing acoustic end-to-end because it's not all rosy, but it certainly is quite a cool setup that helps us out in a lot of different ways. One of the key things that we'll talk about is the principle of time-synchronous noise compensation. That's what we call TNC for short. And we'll be using a lot of that in today's session. We will cover some of the parameters that are frankly impossible for us to measure without TNC. And then we'll talk about some practical examples. We'll share some practical examples of where we have used TNC to get some really cool data from our test setup. Then we'll wrap things up and send you guys on your way. Now, if we just take a look at the real life communication scenario, what we end up having is two people on a phone call. They each have their own devices. Those devices have mics and speakers, and they're communicating over a network. I don't think there's any surprise there. We've all done that. Now, what we want to accomplish then is when we have that communication path from one side to the other, from a test perspective, what we normally do is we end up replacing the near end user with a HATS and the entire network second DUT and far end user we replace with a measurement and analysis system. So of course in the head acoustics domain we talk about Aqua and we talk about the lab core from the far end side, and then the near end side we have our head and torso. The head and torso of course does a great job of representing us, at least acoustically, in the sound field and interacting with the device acoustically. So just from a high level perspective, one of the cool things about the traditional way of doing things is we can completely isolate one device at a time and focus on its performance, both from a tuning, testing, validation perspective. The near end user, as I mentioned, is replaced by the head and torso, and the far end signals all originate in the measurement system. Now, the two types of signals that we are interested in analyzing in this case is going to be, from the perspective of the device under test, the sending signal and the receiving signal. The sending signal, of course, it originates from the measurement and analysis system, but we transmit that signal to the mouth of the head and torso. The mouth of the head and torso speaks, and our device microphone picks up that signal, processes it, and sends it back to the measurement system for analysis. That's the sending direction path. That's highlighted in green on the slides. The other direction, the receive direction, is we're transmitting a signal from the measurement system to the device. The device receives that signal, processes it, and displays it to an ear or both ears of the head and torso. Those are the acoustic signals that we capture, send back to the measurement system, and we analyze. Those are the receive direction signals. That's all good and well. Then we can also add background noise in the lab. Of course, this is completely synchronized. We have different standards that we can refer to that allows us to actually reproduce these background noises to a very high degree of accuracy. Now, the bigger question, and really why we're gathered today, is to talk about why we need acoustic end-to-end testing. The short answer is it's not always possible for us to cut the system in half, intercept all the signals halfway through the network path or in the electrical path. And for whatever reason, we'll mention some of them here, the acoustic end-to-end signal is just our only option to measure these systems. So the first scenario that we run into, the most common one, is simply that the systems that we're trying to test use proprietary protocols and codecs where we do not have a reference client that can act as that transparent far end part of the system. And so we see this in a lot of voice over IP clients and some conferencing systems where there's just no way to intercept, to send and receive signals to our device under test. We have to go with the full acoustic end-to-end setup. Another one is when we run into systems that use a very hard form of encryption. This is typically found in the first responder community, so police, military, rescue services. We don't, again, have a way to intercept those audio signals, so we have to get two of the devices, two different rooms, and do the full acoustic end-to-end testing. And the final one is going to be when we have systems that are completely hardwired. And the typical examples we see of those are the types of devices that are installed in buildings for intercom system, things like door phones. We also have similar types of systems, but more in a medical or in a hospital setting where we just don't have a way of cutting that system in two. And similarly in things like elevators or other emergency type intercom systems, the only way to go about testing those accurately is to simply use the full system end to end, and we need to go with two hidden torsos and two chambers. And that nicely dovetails into this next slide, because the main challenge regarding acoustic end-to-end testing is going to be that we require two head and torso simulators, one on either end, to interact with each of the devices. We need two devices, and of course we need two separate rooms, because we don't want the two sides of the phone call, as it were, to be disturbing each other from an acoustic standpoint. However, one of the great things is we don't have any need for complex reference clients or radio testers. This is a straight up use the device as they are, as they come commercially off the shelf, place them in a phone call on the live network, and you test, which makes it, from an operator standpoint, actually fairly straightforward. Now, the challenges that we also face once we've acquired our gear and our setup is that for some test cases, the acoustic signals that are present in the room during testing are also acoustic signals that are going to disturb or disrupt our analysis. And the two typical examples of those are going to be background noise that mask or cover the signal that we want to measure. Typical example of that is measuring the receive loudness rating in the presence of noise. And then we also have the near-end talker's very own voice, so the acoustic side tone of the talker that's covering the signals that we want to measure. So in this case, a typical example is, for instance, echo, where the side tone is going to be a big issue if we're trying to monitor any echo signals coming from our device. In both cases, though, we do have a way out. That way out, that get out of jail free card, is called TNC, time-synchronous noise compensation. Now, enough about the challenges. Let's take a quick look at some of the benefits. And flat out, the biggest one is acoustic end-to-end testing allows us to measure certain communication systems that we otherwise simply would not be able to do. So if all else fails, great news, we have acoustic end-to-end testing that allows us to test these devices, and they can be done in a completely black box type of environment. As I mentioned before, we simply just take the devices as they are and place them in a call, and off we go. We don't need to do any configuration. We don't need to mess around with codecs and protocols and radio testers and other things that usually trip up people when we are doing acoustic validation of communication devices. And once you have this set up, once you have your two end torsos and your two chambers, the beautiful thing is your rooms are ready to go for any type of device. It could be voice over IP, it could be mobile phone. It doesn't really matter to us. It could be hands-free, handset. You're good to go. Now, from a measurement procedure standpoint, as I mentioned, there's a lot of challenges. I think, or fewer challenges with acoustic end-to-end. The one thing that really we just need to be very cognizant of is the fact that we get our synchronization done correctly. Now, if you use a established test system like Aqua, a lot of those things are handled for us, but that's the one thing we really need to be aware of. And because we're doing acoustic end-to-end, we have background noise playing, the results that we're getting are actually going to be awfully close to the real-life user experience. So that's a bonus. Now, let's take a look at how well the acoustic end-to-end setup works. The way that we want to do that is we take a fundamental parameter like frequency response, and we want to measure the frequency response of the system in an end-to-end scenario and in a traditional electric to acoustic scenario. So in the middle, you see a big blue box and it says making an end-to-end measurement. There's a straight line. We do it one shot, we're done, right? You send a signal out of the HDUT's mouth. Device 1 picks that up, encodes it. After all the processing is done, sends it to device 2, decodes it, and plays that out to the ears of the head and torso on the far end. And now we have a complete system level frequency response. If we had to do that the traditional way, we would have to, at a minimum, well, one way to do this is to break it up into 2 steps. Number 1 is first we have to make a sending direction measurement that's shown in the green box in the bottom left. That sending direction result we will have to reuse and apply as the stimulus for the receive direction measurement, which is step 2 in the bottom right side. And with that, we end up with essentially a view of the system level frequency response. Now, just to give you a practical reference point, what we see is in the top left-hand corner, we have the sending frequency response of our given device in the traditional way, the electric to acoustic testing. So no news there. This is a typical send frequency response. Now, if we take that send frequency response or that send signal and we use that as the stimulus in our receive direction, what we end up with is the plot in the middle there shown in red. And if we did the acoustic end-to-end using 2 of the same devices, what we end up with is something that looks like that. Now, quick look at it from those offset angles, they actually look really, really good and really close. And just to do it one better, here they are overlaid, and you can see when we use the traditional method, breaking it up into 2 steps versus just doing a one-shot acoustic end-to-end, we actually have a really good match between the 2 setups. So certainly we have confidence that not only does the acoustic end-to-end work, but the traditional method works as well for gauging the system level response. So here's the big question. Assume that we have a device that we want to place in a noisy environment. It could be a mobile phone, it could be a conferencing device, doesn't really matter, but we want to place this device in a noisy environment and we want to figure out, does this device change its behavior depending on the background noise? So the way that we would go about doing this is we would look at the level and spectrum to investigate if there are any differences. Now, the only way to go about doing this measurement is to place the device in background noise. We'll put it in our chamber and start the background noise system. Now, of course, the first problem we run into is that background noise is going to mask a lot of the output from our device. In other words, we have really bad signal to noise ratio. It's going to be hard for us to gauge level and spectrum of the output signal of that device. The other challenge that we had is that what we call the regular or traditional calculation algorithms, such as receive loudness rating, those algorithms are just not equipped to separate between noise and signal. So, rhetorical question, how do we remove this unwanted signal? We use TNC. Now, bear with me here, there's quite a bit to cover, but we have a chamber on the left-hand side. That chamber has a device under test, and we will transmit a far-end signal to our near-end device, and that device will play out what we would call the receive signal. It's shown in red to help emphasize that this is a receive direction test, and we will measure that receive direction signal using the ears of the head and torso. At the same time, we will have our background noise system pumping in whatever type of noise, pub noise, car noise, you name it. That's shown in purple. So in the bottom left, what we end up with is this gray, murky mix of background noise and device playback. Now, in that same chamber, shown in the middle, we now disable the playback of the DUT, or simply stop transmitting anything, and we only play the background noise, and we capture the background noise only using the ears of the head and torso. That is the purple trace shown down here. And this is where the synchronization becomes hugely important, because what we're doing is we're capturing level versus time traces, right? We're working in the time domain, and TNC is essentially a time domain subtraction. If we are to do this time domain subtraction accurately, we need to ensure that all of our signals are going to be triggered at an appropriate time to a bit level accuracy, so that when we do that time domain subtraction, we have confidence that the background noise that we measure here is removed from that gray murky mix, leaving us with the device playback as if the background noise wasn't playing. Hopefully that's clear to everybody. The point is, if we can remove that background noise using TNC to a high enough degree, we can place devices in background noise, have them be exposed to background noise, behave differently, and we can measure them, but we can remove the background noise to measure how the devices adapt to that background noise without the background noise influencing our analysis. Now, usually the rule of thumb that we go by when we're using TNC is we'll have a couple of, let's call them calibration test cases in advance. The rule of thumb that we go by is that TNC needs to remove at least 30 dB of the unwanted noise. In this case, it's background noise, but 30 dB is the threshold, which means when we've done our time domain subtraction and we end up looking at just the device playback, if we assume that at least 30 dB has been removed, we essentially have enough SNR or resolution, in other words, enough confidence that what we're seeing here in the red trace only is truly the device playback with the BGN removed. Let's look at a real-world example. So on the left-hand side, we have that gray murky mix of background noise plus whatever signal was coming from our device under test. And clearly, it's hard for us to separate what is what. If we repeat the measurement, this time the device is off or muted or not functional, and we just measure the background noise shown in purple in the top right, if we have our synchronization done correctly, we can do our time domain subtraction, and what we end up seeing is the near-end signal without the background noise. And you can see clearly in between the pauses of the utterances, background noise has been removed. There is no trace of background noise. Now, that's great because now we can start to look at that signal and say, how does that device perform? The first thing that we would probably do is we would do the measurement again, but this time without background noise, so that we can see, let's look at the device without background noise, just in its normal state. How does it perform? That's shown in blue. That's basically the overlap is shown in black on this trace. Now we can compare what is the effect of the background noise on the processing of the device, not acoustically, but on the processing of the device. You can see that this device is clearly changing behavior in the presence of background noise. That's very visible from the time domain trace. And if we just look at these spectrums, not frequency response, but the spectrums of the resulting signals, so there's been no compensation for the speech signal input here, you can see that for a normally performing device, it's shown in blue, and when the background noise is triggering the processing on the device, there's all kinds of content being added above about 1500 hertz, and there's somewhat of a reduction down at the lower frequencies. Now, without listening to the files and doing more analysis, it's hard to say exactly what the device is doing, but it could be a fairly simple compensation here in the higher frequencies to improve intelligibility. So maybe it's amplifying the speech content up around 3-4K where human ears are very sensitive. That's one guess. It could also just be non-speech-like content. Either way, it maybe sounds tinny. Certainly we've lost some bass response. So the device is clearly changing behavior, and this is definitely the way for us to go about doing it. Now let's switch gears a little bit and look at echo measurements. So a little bit like the background noise scenario, and when we're trying to capture echo, we have the problem that the acoustic side tone, it could be a combination of acoustic and electric, but the side tone in the near end is going to be a challenge. So in this case, for the full acoustic end-to-end, we have 2 chambers set up. The process is the head and torso will speak, that's shown in green, to the device on the near end. We will send a signal to the far end, which will be playing out into the room, and sure enough, there will be some component of echo which is not canceled sufficiently by this far end device, which sends the echo signal back to us, and the echo signal comes out. Now, if we are trying to measure at the ears of the head and torso the echo signal, the challenge is going to be, sort of shown in purple trace here, that we get a lot of acoustic side tone. And so somehow we need to remove that purple trace, the acoustic side tone, so that we can accurately evaluate what the echo components, potential echo components are from the far end device. So, question, how do we do that? We use TNC. So much like before, we will do this full measurement as I just described, and what we end up measuring at the ears of the head and torso is this gray mix of the acoustic side tone plus any potential echo components coming from the device under test. Now, let's repeat the measurement, but in this case, we don't even have to place a call. We can switch off the device or even remove the device for that matter, because all we're interested in capturing is the unwanted acoustic signal. In this case, it's the acoustic side tone. So we just have the hats talk to himself and pick up the signal using the ears. That's the side tone trace. And when we do the time domain subtraction, which is the key in TNC, what we end up with is a very good representation of that potential echo signal that comes back. Now in this case, hopefully it's super duper low because we don't want to see echo, but that's the general idea. And of course, again, because we're doing time domain subtraction, I can't emphasize enough that we need to have very strict control over the synchronization of our test signals. Now, just to make a little bit of a lateral jump here, I do want to just mention that for a handset setup, there is no reason why we can't use TNC in this case either. The difference is, though, that instead of acoustic side tone only, you know that when you place something like a mobile phone or a handset up to your ears, there's also an electric side tone path that occurs in that mobile phone or in that handset device. So we're not just wanting to remove the acoustic side tone, sometimes known as acoustic leakage, but we also want to measure and eliminate the electric side tone so that we can gauge the potential echo signal coming from the far end. The main difference is when we do this for handset mode, this handset does have to be placed in a call because then we otherwise don't get the electric side tone in the device. We would only capture the acoustic side tone, and when we do the time novel domain subtraction, it wouldn't be correct. So this device needs to be placed in a call. Now, from a practical perspective, let's go through this process again. What we have is a trace that shows side tone plus the far end echo signal. And of course, this is going to be impossible for us to detect where there might be echo in this area. Now, if we then do the side tone measurement only, we can do our time domain subtraction, and we end up with revealing that our far end device does in fact have some echo burst, specifically right here at the 15-second mark, which is now being revealed to us. If we then do a quick analysis, say echo loss or TCLW, it gives us about 39 dB here. That's equivalently measured by the eQuest metric to give us a 3.3 score. That seems fairly reasonable for those type of echo loss numbers and looking at it. If we were doing the full acoustic end-to-end setup and not using TNC to remove the acoustic side tone, well, because the acoustic side tone is so dominant, the echo loss would be 8 dB, which is terrible. Sure enough, eQuest is going to punish us. This is not the way forward. Now, I just want to drop in a note that eQuest actually has a built-in side tone model, which is currently functional for handset mode. And right now there is work underway where eQuest is then being adapted to have side tone models that are capable of working for all kinds of end-to-end scenarios. And specifically, it's the hands-free scenario, which is the interesting one where you have both ears open. Now, let's look at some of the challenges. So first of all, especially when we're doing echo measurements, one of the challenges is that we have a very, very low signal-to-noise ratio between the useful signal and the annoying signal that we want to remove. So we're starting off in a bad spot, right? We have bad SNR. And then, unfortunately, the channel noise, so not the acoustic noise, but the channel noise that occurs on our transmission path, it is going to be random, and we cannot subtract that out using TNC. In fact, what we end up doing is we actually end up doubling that noise. Now, fortunately for us, that channel noise is relatively low level, but those two factors combined does mean that there are some limitations. Normally, it means that we have more than enough clarity to show if there's a problem with the device. So if you recall in previous online seminars, we've used this grading scale of going from 2 negatives all the way up to 2 positives. The thing that we need to be aware of is if we have a terrible device, acoustic end-to-end testing will undoubtedly allow us to reveal that there is an issue with that terrible device. Even if it's a moderately bad device or an average device, no problem. We can detect the errors that are occurring in the echo cancel performance using end-to-end testing. Now, the challenge is once we get into the sort of good to very good territory, it's going to be very difficult for us to differentiate between those devices using acoustic end-to-end simply because of the challenges that we're facing here. Now, let's look at double talk using the acoustic end-to-end setup. The challenge here is when we're evaluating the double talk scenario, the near-end talker is going to be influencing our measurements. So the problem is essentially the same as what we had when we were doing our echo measurements. And sure enough, the solution is going to be the same as when we were doing the acoustic end-to-end measurement. I don't think there's many surprises there. Now let's look at a couple of examples. So we have 3 different tests that were done. So on the far left, we can see a far end device, which was a handset in handset mode being played out at nominal volume. It performs well from a time domain examination. And we can even pull up the scores to show you it's performing really well. When we have our far end device in hands-free modes at low volumes and max volumes, well, we get different degrees of degradation for our double talk example. Now, let's look at how TNC affects the double talk analysis. Because if we just focus on the left-hand side of the page, you can see an awful mix of traces. And in gray, we have the double talk signal plus the near-end speech. And the problem we have, of course, is that the near-end speech covers the signal that we are receiving from the far end. So when we do the delta level versus time analysis in the bottom left, you can see because the near-end speech is so dominant, there's barely any difference between the single talk and the double talk. As a result, we vastly overestimate the double talk performance. In other words, it's way too optimistic. We're not actually that good. Now, if we do use TNC, so if you focus on the right-hand side, now that we've removed all the near-end speech, we can actually much better see what the double talk performance is like. It's shown in blue, or wherever we have overlap, it's shown in black. And sure enough, if you recall the structure of the double talk test, we have 8 utterances of the word 5, and then we have some full Harvard sentences. Clearly, there's a bunch of these utterances, 5, that are not showing up. That's not at all visible here, but it is here. Likewise, for the full Harvard sentences, okay, we're not getting perfect or great performance. The delta level versus time analysis shows us as well that we're getting a lot of attenuation. And when we do that analysis, you can see what was previously thought of as a fantastic type 1, less than 3 dB attenuation type device. Well, it's maybe not that rosy because we're looking at something more akin to a type 2B, somewhere around 8 to 8.5 dB of attenuation. So TNC is hugely important and can benefit us for double talk analysis as well. So let's discard the left-hand side and then let's just focus on the results from the right-hand side. Now, let's see if we can wrap this thing up. The messages that we wanted to convey to you today was really that acoustic end-to-end testing gives us possibilities to measure these communication systems that we otherwise couldn't. And we gave some examples of typical scenarios of where we just can't access these devices in the traditional way. And while there is a requirement for more test equipment in terms of test chambers and head and torsos, there is the benefit that we don't need complicated network simulation tools. And once we have that set up, it is universally applicable. Any 2 devices that can make phone calls, we can use in that system. It could be anything from push to talk to voice over IP to encrypted communications systems. I think the third message here is TNC is the way to remove signals that otherwise would make the analysis impossible. And we talked about using it for BGN. We talked about using it for acoustic side tone and for acoustic and electric side tone. Now, I just want to mention that TNC isn't necessarily a miracle cure. It does a great job and it helps us in these situations. But what would be even better from a longer term perspective is that if our traditional methods were simply smarter and could differentiate between the unwanted signals and the desired signals, so that we didn't have to go the route of using TNC. Now, the restrictions that we have, of course, is that as much as we try, there are still some details that do get buried in bad SNR situations. Sometimes we have details that get buried because of the increased channel noise floor, and that limits our ability to really differentiate between the super high-end products. And that's just the way the situation is. And of course, because we are doing full end-to-end testing, we are not able to necessarily differentiate between what processing is taking place in the sending direction versus the receiving direction, because they're both mixed together. So as long as we are clear on those restrictions, as long as we are clear on all those benefits, the point is that acoustic end-to-end testing allows us to do things that we were otherwise unable to do and serves us really well in supporting that. So, couple reminders. We have a microsite dedicated to audio conferencing solutions. Go visit there to get access to a lot of this content. And then we have the next online seminar in the series showing up on September 1st. I would strongly encourage you to sign up for that. And then with that, I would like to say thank you very much for attending, and I will open the floor for questions. Thanks a lot.